just joined. Cool.
Okay. Hello, students. Let me send you a link to the slides. Oh, sorry. Well, they're online, linked from our website, but here's you have a direct link on the chat. Okay. Let's go to the slides. Okay. One moment. Okay, here we go. So grading and testing. So you sorry, what do you want to know?
When do you expect the grades to be released for the exam?
We barely started. It will take us a while, like counted week, no less.
All right, thank you.
Okay. So I mean, the biggest part is that we have to make sure that we are assigning partial credit correctly, and these things are open-ended. So there's going to be many cases where there is partial credit that is not so obvious, and so yeah. So that's why it takes time there. So yeah, we have different views on like how to assign partial credit among ourselves. So discussions. Yeah, and we will. So Will has posted some solutions on Piazza for some problems. I will post for others if so you know. We can also post some things like, okay, here is the solutions is not quite there. You know, roughly how bad would that be if your solution was like that, and things like this. Okay. This kind of problem may appear on the optional final for students who take it. I don't know what you mean.
I was saying that there may be a linear homogeneous question on your comprehensive final for the students who take the optional final.
Since again, you just mean that there's a linear homogeneous recurrence relation on the final?
No, I'm saying there may be, just because like what you've told me and the other TAs about what you plan to put on the final and it being comprehensive. I was just saying.
Yeah. Oh yeah. Well, okay. Yeah, it's totally game, right? Like, I mean, it's part of the class, so yeah. So it's it can be on the final. I mean, everything from the class can be on the final, right? So in particular, everything from the test, from so if anything is on any test, then you can safely assume that exactly that kind of stuff is on the final as well. But of course, final is limited in time, so I cannot ask everything from every test. But like if you're studying for the final, then the first thing you should review is whether you can do the kind of problems that were on all the tests. Well, anyway, but that's jumping ahead. So let's go to our to the material we have. Hold on. So this camera just films my hand, and maybe it's better to film my face. There's different opinions on that. Okay, so let's go with the stuff. So we're continuing modular arithmetics, and that's roughly where we are in the material in the book. And now I haven't opened the exercises, so but I will open them, or like every other one, so you can practice the stuff as you read. So here is so we have a notion of modular arithmetics introduced a week ago now, so you might be forgetting, but when you do a modular reduction, you can multiply and add, and all the operations make sense. They are just cyclical in nature. So you cut off integers modulo sum modulus, and you just look at the remainders of these integers modulo to modulus. So this is related to the concept of that one number divides the other. So we say that x evenly divides y if some integer m multiply m by x gives y. We denote it this way. So this is read x divides y. And by divides, we mean evenly divides. Okay? So another way to say it is that y is an integer multiple of x, or simply multiple of x. And conversely, x is called a factor of y. Now using the modulus operations, we'll say that another way to say it, that x divides y, is to say that y modulus x is 0, right? Because if x divides y exactly, then if you do integer division, the remainder of this division will be 0. So that's yet another way to say the same thing, right? That y modulo x is 0. I will add this to the slide later. A number is a prime if it doesn't have any non-trivial divisors. In other words, it's an integer and it's greater than 1. So by convention, we don't treat 1 as a prime. But every higher integer, which has the only positive factors of it, are simply 1 and the integer itself. These are trivial factors because for every x divides itself, right? X always evenly divides x. And also 1 always evenly divides everything. So these are not interesting divisors. And a prime is a number that doesn't have any non-trivial divisors. The opposite thing, if n is not a prime, then we call it composite. So if some integer can be expressed as a product of other integers, right? Because p, if it only is divisible by 1 and p, so it can be expressed as 1 times p, but that's not an interesting thing. It's one of these factors is p itself. A composite can be expressed as a product of integers which are different than itself. And yeah, so that's a composite. If you continue this, so you take a number and you decide it's not a prime, so it has some non-trivial factors. You divide this and you could represent it as a product of these two non-trivial factors. Now you can look at these factors as this prime. If one of them is not, you can factorize it further. This creates like a tree of factorization, right? Your top numbers that you start with, the leaves are factors such that if you take a product of all the leaves, you're getting the number. And also everywhere you go up the tree, two factors multiply, you get the parent node, right? So children are factors. The parent is the product of these children. The leaves are all factors. The question is, if you do it with an integer, well, maybe you're gonna get the leaves in different order. But let's say you order them from the smallest to the largest, right? Because for every tree, you can switch the left and right tree branches. Eventually, after you do enough of these switches, you can order from the left to the right. Is this unique? Can you factorize somehow differently and arrive with a different sequence of primes that produce an integer? Of course not, right? This is a unique process, so it does not matter in what order you do it. The primes that are the leaves of this factorization tree are always the same. So this is a fundamental theorem of arithmetic. Every integer has a unique prime factorization up to ordering. But if you order from smallest prime to largest, it's unique. Now, some prime factors might appear many times, right? Like 8 is 2 times 2 times 2. So, if you just write them in a non-decreasing order, so 2 times 2 times 2 is the same, and then you increase to 3, increase to 5. Here's an example of a full factorization of 120. When we look at integers, an interesting question also is, if you're given 2 integers, what factorizations they have in common? If there are 2 different primes, they have nothing in common. The only factor they have in common is 1. That's a trivial one, it doesn't count. But other integers must have a lot of factors in common. The factors that 2 integers have in common come into the concept of greatest common divisor. Because what is the greatest common divisor? It's the largest integer that evenly divides both numbers, x and y. And if, okay, so if I do full factorization of x and a full factorization of y, the greatest common divisor is going to be a product of all the primes that full factorization of x and a full factorization of y have in common, right? So that's going to be the GCD between 2 numbers. If this set of common prime factors is empty, there is no common prime, right? Then, well, there is a trivial element that is common. It's a 1. So GCD of 2 numbers, if that happens, is 1. We call those 2 numbers relatively prime. So, for example, 8 and 9, they're both non-prime. 8 is divisible by 2, 9 is divisible by 3, but they're relatively prime. They have no common factors. Or 9 and 25, etc. They are relatively prime. Sort of counterpoint concept. If you look at the tree of factorization, you factorize x, and if you group all the factors, and you factorize y, and you can group all the factors that x and y have in common, and that will be a GCD between x and y. You can go into the tree of factorizations up like follows. You can ask, you start with x and y, and say, what is the smallest number such that x and y are both factors of that number? So if I multiply x by something and I multiply y by something, I will have a common, they will meet on the tree of factorizations above. That's called the least common multiple. The minimum such number that both x and y divide that number, that's called the least common multiple, denoted LCM. And here is the interesting thing. If you product of 2 numbers x and y, if you find the greatest common divisor and you find the least common multiple, the product of x and y and the product of the GCD and LCM must be equal. Why is this? So, okay, let's do it by, proof by example, but you can do the general one. So you have some number. Here is a factorization of it. It's 3 times 3, then 4 multiples of 5, then a 7, and then an 11. Okay, so somebody asked if that applies to prime numbers. Yes, it does. It applies to all numbers. If the two numbers are prime, x and y, what are all these things? This is just x and y. What is the GCD of two prime numbers? It's a 1. What is the least common multiplier of two prime numbers? It's the two numbers multiplied, right? If x and y are both prime, LCM is just x times y. There is no other way to multiply x by something, so it's divisible by y. And there's also no other way to multiply y by something, so it's divisible by x. The smallest such number is just the product of the two primes. So this will be maintained. Okay, now so here is one number. Here is a particular factorization of it, and here is another number, and it's factorization. Some of these factors are common. 3 is a common factor, but not just that. It's 2 3s, right? It's a 3 times 3 that is a common factor between these two, because both this is divisible by 9, and so is this, because it's 3 times 3 times 3 times 3 times 3, right? Also, a single 5 divides both, but higher powers of 3 divide this number, but not this one. And higher powers of 5 will divide this number, but not this one. And these factors are not common ones. So the GCD, what will it look like? It will be 3 to the power of 2, because that divides both this and that. And it will be 5 to the power of 1, because it will divide this and that, but no higher power of 5 will divide both of them. And any other prime factors will not divide both of them. If they don't appear on this list, then they don't divide either. And if they do appear, but only in the top row, then, well, they don't divide this guy, and vice versa. So the GCD is just 3 to the second power and 5 to the first. Least common multiplier. What is the number, the smallest number you have to multiply this thing to be divisible by this? Well, you have to multiply by 3 to the third. Okay, and to get here, because this one will become 3 to the fifth. Here, it's this guy who has to hike up. He has to be multiplied by 5 to the third to become 5 to the fourth. 7, well, this guy has to be multiplied in order to hit here. And 11 the same, and 13 to the second. So this is the LCM. This is the smallest integer, which both these, all of these are factors here, and all of these. And you can see that if I multiply these two, and I multiply these two, I get the same thing. This is 3 to the second, 3 to the fifth, 3 to the second, 3 to the fifth. 5 to the fourth, 5 to the first, 5 to the fourth, 5 to the first, and all the other factors appear. Why? GCD is this factorization to the powers that are always minimum of the two. So if 3 appeared with multiplicity 2 in one and 5 the other, you take the minimum. 5 appeared with multiplicity 4 and 1, you take the minimum. 7 appeared with multiplicity 1 and 0 in the other, you take the minimum. There is no 7. 11 the same. 13 has a 0 multiplicity here. You took the minimum implicitly. LCM It's the same, but taking maximum. And so the reason that they always multiply is simply because if you take a minimum of two numbers and then maximum and add, you're getting the two numbers always, right? And when you multiply something that looks base to some exponent I times the same base to exponent j, what happens is that you add in the exponents, right? This is 3 to I plus j. Okay, so that's why this holds. Okay, so will you be expected to find full factorization? No, only if it's small enough, so that the understanding is like that you need to we need to test that you understand what the factorization is. So we'll give you something relatively easy to factorize, like 150. Okay, not like some huge number. We don't want you to use calculators. This is not the point. So, okay. So you can, you have this structure on arithmetics, on integers. Who divides whom? Do they have common divisors? Well, how do you tell what a divisors of a given integers are, right? So how did I arrive at Archie's prime factorization of this number? Well, I arrived at it because I actually created this and then multiplied to go this way. But if you were faced with the question, how do you go this way? Well, you need to factorize. You're given an integer, you have to find its factors. So a question arises, how do you factorize? Here is a brute force algorithm. You need to find factors of n. Well, just take a loop, going from 2 to all the way to the n-1, and check whether integer division of n by x gives you a round, round number. And if you find factors, you output them, and if you didn't, you say that the number is prime. So this is a primality tester and also a factorization algorithm. Well, you can do it much faster than that, right? Because by the time you reach square root of n, you can stop searching. If you haven't found anything, you can stop searching. Because if a number has some non-trivial factors, one of them has to be at most square root of n, right? It cannot be both larger than square root of n, or otherwise multiplied, they will give you bigger than n. So I can only go to square root of n if I so feel. Problem with this is that if n is really large, like numbers that are used for cryptography, so your modulus in an RSA crypto system, the number of digits is a number going to hundreds. So if n has 200 digits, so it's basically 10 to the power of 200, roughly, right? Then square root of n will have 100 digits, right? Because if to express a number that is 2 to the power of 200, if you take the square root of that, it becomes roughly 2 to the 100. Because when you take a square root, right, you divide the exponent by 2. So, but that is still a huge, so if you have a loop that goes to a 100-digit number, then it performs 2 to the 100 operations, 10 to the 100 operations. And 10 to the power 100
Professor?
is what?
Professor, sorry to disturb. Are we on, which slide are we on?
Which what?
Which slide are we on? Are we on the what are GCD, LCM? Are we on that slide? Or?
Oh, do you not see my slides?
I see the slide with the GCD and LCM. On the bottom, there's min plus max.
Okay, wait. How did that? So my slides are not moving?
I don't think so.
Yes, they
It
seem
seems to be the
frozen.
case if you're not on
Okay.
the
Yeah, I don't
GCM
know
and
what happened. Like
LCM.
they're moving. So I'll stop sharing and then share again. So the last slide was this one.
Yeah, we can see it now.
Okay, and then sorry. Thank you for pointing this out. Yeah, I don't know how that happened. Well, all right. So sorry about that. Okay, so this is the loop that I was talking about. In order to determine whether a number is prime, you just cycle through all possible divisors and you test whether it evenly divides or not. You can do this better by just searching up to square root of n, right? Because if you haven't found a factor and you reach square root of n, you can say, okay, this is a prime number. But if n has 200 digits, then square root of n has 100 digits. And right, because 10 to the 200 square root is 10 to the 200 divided by 2. So that's 10 to the 100, and therefore you can write it using 100 digits. We'll look at the length of different representations in a few lectures. So a student says, why don't you just go in a loop and only check for prime factors? Well, good, but that's the point. We wanted to be able to determine whether a number is prime. So inside of this loop, you're going to have a little test whether you will determine whether x is prime. Well, then you're just recursing, right? So I doubt this will give you a faster algorithm in the end. If you're recursing back to this test, but now for every x. So you might want, of course you can do something better. You avoid even numbers. You avoid numbers multiple by 3. You can avoid multiple by 5 and so forth. The thing is, well, how eventually you will have to enumerate all primes that are smaller than 10 to the 100. That's too big of a list, right? So, so this kind of loop, if it takes 10 to the 100, that's too much. Even when every operation takes a nanosecond, there is not enough nanoseconds in a year. There's basically around 10 to the 18 only. So this number of, would take you 10 to the 82 years. The problem is that this is an exponential in the number of digits, right? So the time is 2 to the, then if you call number of digits k, then this efficiency of this algorithm is 2 to the, okay, it's exponential, so 10 to k over 2. It doesn't matter that it's a base 10 or base 2. These are just multiplicative factors. It doesn't so much matter that you are taking not exactly the number of digits, but dividing it by 2. It's still exponential in the number of digits. And any such algorithm will not work on large numbers. Okay, you can just take a larger, high enough. And in fact, for crypto systems like RSA, this comes in. They are way too large to perform such algorithms. So, but here is a slight difference in this question. So this algorithm, the loop, it both told you whether the number is prime or not, and if it's not, then it found the factors. you can separate these two problems. The basic one is primality testing. This is a problem which just tells you, okay, you have an integer. Tell me if it's a prime, if it's prime or not. If it's not, you don't have to give me the factors. You just have to tell me yes or no. Factoring is a harder, potentially harder problem. It's not enough to decide. You also have to find the factors. This is in computer science known as decision problem, and this is known as search problem. Equivalent, we have this in computing all over the place. You can ask a given formula, Boolean formula, if it's complicated, has tons of variables. Tell me, does there exist a satisfying assignment to this formula? Is there any way to instantiate the variables so that the formula will evaluate to true? That's a decision problem. Search problem, find the assignment that makes the formula true. There might be heuristics that will tell you that the formula is true without finding the assignment. Some problems, the decision and search are not equivalent. We know algorithms to decide, but without explicitly finding the witness, so to speak, that would say, okay, now if I tell you, yes, it is prime, it is composite. And you say, well, give me a witness for it. So give me the factor. I say, well, that I cannot do. I don't know how to do. But I will tell you that it's prime, that is composite. It's a little surprising. Like, how can you know that it is prime or not without knowing the factors? And the funny thing is that there is a distance between these problems. So whereas factoring, we do not know, and we don't believe that the classic computing, in other words, classic Turing machine, to which every hardware and every software is, however powerful, is equivalent, essentially, that there is going to be a polynomial time algorithm for factoring. What would that mean? It's algorithm is polynomial time if given any integer, it successfully outputs prime if it's a prime and factors if it's a composite. And moreover, it works in time that is polynomial in the length of the problem. So it's always not the integer itself, it's the length of its description. If you think, this is always like how you think of the running time of algorithm. If you're given a list to sort, what is the parameter that determines running time? It's the length of the list. It's not like how big the integers on it are. It's the length. So it's the same for all the problems. Solving a Boolean formula, it's the length of the Boolean formula. For factoring, it's the length of the integer. In other words, the number of digits in it. And this algorithm here was exponential in the number of digits. It worked in time 10 to the 100, where 100 was length of digits, right? I mean, divided by 2, but that doesn't matter. It was not polynomial, so it was not that I can take some number of digits and take it to some fixed power, quadratic, cubic, whatever, but it's a fixed power. So on 100, on integers that have 100 digits, it would run with time 100 to the d. Perhaps d is high, but that's much better than time 10 to the power of 100. Okay? And there is no such algorithms known, and we don't believe they exist. On the other hand, with quantum computers, at least for a quantum, the ideal model of quantum computing, there is algorithms. It was one of the first algorithms for quantum computers shown by Shor, that you can factorize if you had a true quantum computer. Quantum computers are being developed. We don't know, will they scale, will they not scale? So still the game is still on. But if they really come into being and they can solve problems on large inputs, they will implement Shor algorithm, and they will factorize in quantum, using quantum computing in polynomial time. For classical computing, is not known and is not believed. No mathematician believes that there is a polynomial time, or if they do believe it, they're silent about that belief. By contrast, primality testing, if you, instead of asking us to find you the factors, you just ask us a yes or no. Does it have any or does it not? And if it does, you don't have to show me. Surprisingly, this problem can be solved in polynomial time. So there is algorithms which will run in time that is not linear, but quadratic, actually, of the digits, of the number of digits. And they will tell you whether the input is prime or composite. And for the longest time, they were probabilistic, not only in that the algorithm made random choices, and based on these random choices, based on these random choices, its answer, so its answer was only correct with certain probability over these random choices. However, it skewed always in the correct direction. So the exact thing was that if the algorithm, if the number was prime, it never said that the number is composite. There was no randomized execution such that it could say the number is composite. It always said, no, the number is prime. But if it's composite, it could say prime or composite, it would probably 50-50. So what did we do? We ran these algorithms 100 times. Because if 100 random executions, each of them told you it's prime, then its only probability 1/2 times 1/2 times 1/2, 100 times, that's 2 to the minus 100. That's a tiny probability, right? That's the kind of probability that, all hardware explodes, okay, with that probability. So it doesn't matter. But if at least one execution told you it's composite, then you just said, okay, it's composite. It has to, because if it was prime, it never answered that way. Okay, so it was in probabilistic algorithms. In practice, it doesn't matter, but still it wasn't like sort of satisfying. And then Indian mathematician whose name I forget came out about 15 years ago with a deterministic primality testing. So the algorithm makes not even a tiny probability that it gives you an erratic answer. This deterministic algorithm was beautiful and it was a breakthrough. On the other hand, everybody still runs Cs because they are faster, and it doesn't matter if you make a mistake if the probability of this mistake is 2 to the minus 100. Okay. So how do we find prime numbers in practice? If you followed my advice, and in the last lecture, I showed you a multiplication table mod 5 and a multiplication table mod 6. And I said, draw a contrast, do mod 6 on your own. You will see that it doesn't work so nicely. This we'll come back to this, but it will be, the effect will be that if a modulus is composite, there are some, it doesn't work so nicely for a lot of things that we want to do. If its modulus is prime, everything works smoothly and beautifully. So in order to pick this modulus for crypto systems, we need to know, is it prime or is not prime? So the question is, how do we pick random prime numbers? And so this is how we do it. We pick a random number and we run a primality tester to see if the number is prime or not. that primality tester takes its time because it has a little probabilistic loop inside. It has to run it 100 times. So you shouldn't pick those primes too often. This is why picking public parameters in a public crypto system is actually the biggest bottleneck of these crypto systems. If you have a system where everybody picks public keys all the time, it's going to be a horrid thing for performance. Public keys should be picked infrequently, published, and that's what they're optimized for, because testing primality takes a while. So we pick a random number, we test primality, and hopefully, if the primality says yes, we're happy. But how efficient can this run? Well, it depends on the following. Because if it says composite, then we recurse. We pick another random number, and we test it as well again. And if it says composite, we recurse. So how long will we run? Depends on the density of prime numbers in general interval range, right? Because if you're picking 200 number, well, you could pick from 1 to 10 to the 200, except that you won't, right? You wouldn't pick the most important digit non-zero, right? Because then it's not going to be 200 digits if the first digit is 0. Okay, but all the other digits, you just pick them at random. So you're sampling from a random number between 10 to the 199 and 10 to the 200. And question is, how many of these numbers are prime? Because if there's only very few, then this loop is going to go and go and go. So here is the beautiful theorem that already was observed by the Greeks, that first of all, there is infinite number of primes. That is a kind of, okay, that's a kind of a mind twister. How do you convince yourself that primes don't end? That there might, whenever you say, okay, there's finite number of primes, that you will contradict this, that if by that assumption, you will be able to construct a number that is higher and must be prime as well. Okay, so that's a brain twister. You can search for the proof yourself. You can look at Wikipedia for it. But not only we want primes not to end, we want them to be easy to find. And for that, we need the density of primes to be significant, so that when you pick a random number, the probability that it's prime is significant. So this loop will tell us yes with significant probability, so that we don't have to repeat it too much. Okay, here is the theorem. Is that if you let pi of x be the number of primes in this interval integer range, in other words, the pi of x divided by x is the density, right? If there is pi of x primes here, then the probability, if you choose a random one, it's a prime, it's pi of x divided by x. The theorem is that if you take x large enough and you compare pi of x divided by x and also divided by the logarithm, natural ln stands for natural logarithm of x, so it's logarithm based e. By the way, now is a good, if you skipped in early section the subsection on logarithms and exponentiation, go read that now, because we will use this now all over the place. And you will have to be able to operate with logarithms. And just like you learn how to operate with exponentiation, or you refreshed that material, you should refresh how to use logarithms. Okay, that this approaches a constant. In other words, that the density of primes contained in this interval, when the interval is large enough, can be approximated. It's about 1 over the natural logarithm of the interval n. So we're not going to introduce this notation. We're not going to, if you know what this means, this basically means that this entity approximates, goes to 1. It's as close to 1 as you need for x large enough. Okay, so for x large enough, the density can be approximated in this way. That's all you need to know in this class. Okay, so don't be disturbed if you don't know this notation. And now there's a little caveat. The way we pick a 200, let's say a 200-digit number, it's not really from this range. It's from this range, right? We are going to ignore from 1 to 10 to the 199 because all these numbers correspond to numbers whose leading digit is 0. So they're not really 200-digit numbers. But notice that this range is 90% of this one, right? Because only 1/10 of numbers up to here are lower than this one. So you can actually work this out numerically and convince you that this is true, but you don't have to. You can just take it from me that this approximation works just as well for this range as it does for this one. Okay, so you should use this approximation for x large enough, like of this type, whether you're looking at density of primes in this interval or in this interval, it's for all practical purposes, it's the same. Now, how to compute this? Well, if you look at logarithms, one of the basic things is a sort of chain rule. If you take a logarithm of a number base 10, and that is simply the number of decimal digits in x. So, right, so if an x has 100 digits, logarithm base 10 is 100. There might be, small fractions. So this is only an approximation, right? Like I'm taking a floor in when I speak. But it's really, we're doing approximation here. So this does not matter. And so logarithm-based E is equal to logarithm-based 10 times logarithm-base E of 10. And that's the chain rule of evaluating logarithms. And a logarithm of 10 base E just happens to be this 2.3. So this is the equation that you should use for approximations. If I have to find a 200-digit number, a 200-digit prime, that means that the number of digits is 200. So this is 460. And therefore, the density of primes in this range, I can approximate it as 1 over 460. So roughly, every number I pick is the probability 1 in 460 that it's a prime. So therefore, this loop I have to repeat it on average 460 times. This is again some probabilistic process that I don't expect you to have known that and to be able to operate with that. But in fact, we'll get to real treatment of probability only at the end of this class. But the understanding that if you have a process that gives you a good outcome with probability 1 in something, okay, call that something t. It was 460 in my example. So 1 in t, it gives you a good thing. How many times do I have to repeat this process to expect that I get a good answer? It's the inverse of the probability, is t times. That's in fact where probability comes from. When somebody says that something happens with probability 1 in 2, 1/2, what they mean is that you have to roughly, you're getting a good outcome. You're getting one good outcome if you do 2, if you sample it twice. So the probability of a coin toss that it's a tail, it's 1/2, exactly, because when you do it twice, you should, how many times do I have to run a coin toss to expect a tail? 2. Okay, so people don't have a good, we don't know how do you measure probabilities? How do you measure probabilities in real world? Only from some observation and extrapolating the results, right? And so we don't even have like a great terminology for probability, but the terminology we do have is 1 in 2 or 1 in 6. That's why probabilities are always designated as numbers between 0 and 1, right? Because it's always a fraction expressed as 1 in some number. And at best is 1 in 1, so that's like sure, or 1 in infinity, I guess, and that's a 0. I guess 0 is not 1 in any given number. Okay. So that's why if you have a loop that succeeds with probability 1 in 460, you should expect to repeat it 460 times on average to get a good outcome. That's why it is very time consuming to pick prime numbers. On the other hand, it is polynomial, right? Because it is polynomial time. Because if the probability is 1 over some constant times the number of digits, then the expectation of how many times I need to repeat it is 2.3 times the number of digits. So this loop goes in time linear in the number of digits and the number of times I have to do it. And I argued that the primality testing itself is also polynomial in number of digits, namely quadratic. So what's the total running time of the primality finder of finding a prime? Is cubic in the number of digits, right? The linear number of repetitions, and each test takes quadratic time. That's why it's not super efficient, right? Cubic, when I give you 100 digits, cube of that is 1,000,000. I'm ignoring constants, right? But it is 1,000,000. It gives you intuition that, oh, this is going to take a bit. Still, it is, it's not exponential, right? It's not 2 to the 100. And 1,000,000 of operations, of arithmetic operations, is still doable, right? It's just that this is not something that you want to do every time you send a message. Okay. So I think that was my talk plan was way too ambitious, and this is actually a great place to end. I will open for questions. Sorry, I'm already a few minutes over. If you have some, I see that there was a good discussion on the chat. Okay, I'm trying to read and understand. I saw something earlier, but I cannot understand so quickly. So speak up if you want to say something. Okay, so all right, guys, so I will see you Wednesday. Thanks for attention, and I will open exercises. Stick around, it's beautiful material. Till then.